All right. Hello, class. Good afternoon. I'm sitting here with Hazel, and I started my last class with seeing if we could get Hazel to howl, so I'm going to try it again for this class. Okay, so we'll see if she's going to howl. Ow! 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 Good girl. Good girl. Okay. Okay, Hazel's going back to sleep. Okay. All right. All right, looks like some people are joining, so that's good. Yeah, I apologize for the delay. We had some technical issues with the last lesson, which made it go long. All right. So basically what I'm going to teach you today is how to determine the direction of the induced current. Okay? How to determine the direction of the induced current. So what we learned the past 2 days is that if you have a magnetic flux and the magnetic flux changes, then that will cause an induced EMF, which is basically like a battery in the loop. And then that battery is going to make current flow. And it's important to know which direction the current is going to flow. Okay? So that's what I'll teach you today. I just want to do a review of magnetism. If you recall, electric current is the source of magnetism. So what if I have a loop of wire? Okay. And what if the wire had current flowing this way? So that the current is flowing counterclockwise through the wire. Well, one of the things that I taught you is if you want to know the direction of the magnetic field from a wire, you put your thumb in the direction of the current, okay? And the way that your fingers curl is the way that the magnetic field loops around the wire. So I'm putting my thumb in the direction of the current flow, and you can see that my fingers are curling out of the page. So that means that if this current is flowing in the in this loop of wire, it's going to make a magnetic field that is out of the page. Okay? So the magnetic field from the wire is out of the page. Okay? Similarly, if we have a current flow that is in the clockwise sense, So I put my thumb in the clockwise sense, and you can see that my fingers are curling into the page. So this would create a magnetic field into the page, like so. All right. So I hope that made sense. That's just a review for magnetism. So if we go to Faraday's law of induction, Faraday's law of induction says that the induced EMF is minus the derivative of the magnetic flux with respect to time. And so the key thing here, okay, is this minus sign. This minus sign says that the induced EMF creates a current that resists the change in flux. Okay? So the best way to do this is to just dive into it. Okay? So let's suppose we all right, I think I'm back. So I'm going to keep plugging ahead. So I was saying that you have this loop of wire, and this will be an example. You have a loop of wire, and there's a magnetic field going through it. And this is an external magnetic field. So this is not the magnetic field that is created by the loop itself. So the loop itself can have a current that makes a magnetic field from the wire itself. This is an external magnetic field that is 5 Tesla. Okay? Now, what if, and by the way, we'll say that the area of this loop is 1 square meter, just for simplicity. Now maybe 0.4 seconds later, the magnetic field is now out of the page, but it is stronger. So I'm drawing more dots to indicate that it's stronger. Okay? So now the external field is, okay, the external field is, now it's maybe 11 Tesla, so it's stronger. So we want to figure out what is the direction of the induced current. Well, if we think about it, the current was going out of the page, okay, and now it's even more out of the page. So the change was out of the page. The direction of the change was out of the page, all right? Now, we know that the induced EMF creates a current that resists the change in flux. So because the change was out of the page, the wire is going to have an induced current that resists the change. So we're going to have, because the change was out of the page, to resist that change, the wire is going to create a magnetic field into the page. Okay? So we're going to have a clockwise current that will be induced in this loop. So this is the direction of the induced current. Okay? We could figure out the size of the induced EMF. It's just going to be minus the change in flux divided by the change in time. We're obviously doing an approximation here because, you know, I don't know how the magnetic field changed from here to here. That's, you know, I didn't give B as a function of time, so we're just approximating it here. But we have minus flux final minus flux initial over time elapsed. The magnetic field is perpendicular, so flux is just going to be BA, and we'll assume that n equals 1. So the final flux is 11. The initial flux is 5. And these should be multiplied by the area, which is 1. So it's in general, it's not going to be B final minus B initial. It's going to be flux final minus flux initial, divided by 0.4. Okay, so that gives